So we want to verify the claim that the amount of money spent on donuts differ based on the season a student was born in, spring, summer, autumn, winter, and the data is shown up there. We want to verify the claim that they are different, and we are going to use the norm. Tau 1 equals tau 2 equals tau 3 equals tau 4. That is the effect from each of the 4 samples, treatment effects. At least one of them are different. So how does this work? We have to combine all the observations together. In this case, I just put them all together, and I made sure that there aren't any ties, because we have to do an adjustment if there happens to be ties. So we start ordering things. So this would be 1, rank 1, rank 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What? Oh, 13, 14, 15, 16. Good.
5 or 3.
What?
4 is right next to it.
This one?
Yeah, and then 3 would be actually.
1, 2, 3, 4, 5.
Yeah, there you
4,
go.
5, 6, 7, 8, 9, 10.
Yeah, 13 should be 12.
13 should be 12.
Why should 13 be 12?
Because you don't have
There's
number
no
12.
13.
No, there's no 12.
There is the round 12
11.
is missing.
Yeah, so put your
11,
13.
this should be 12,
Yes. And that's 14 should be 13.
13, 14, 15. I can't even count today. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Good. What was that? Yes. Okay. N1 is 5, N2, 4, N3, 3, N4, 3. Those are simply the number of observations in each of the treatments or samples. Population goes the same. From last time, uppercase N is simply the sum of all the individual sample sizes. That will give us 15. Now we have to find the rank sums for each class or for each treatment. First, for spring, we have to sum all the combined ranks. 6 plus 1, 7, 19, 23, 31. R2 for the second sample, 20. R3, sum of all the combined ranks for the third sample, 14 plus 13 plus 15, 42. R4, 7 plus 9 plus 11, 27. The sum of all ranks must be n times n plus 1 over 2. So n times n plus 1 divided by 2. So total, we have 15. 15 times 15 plus 1, 16 divided by 2. 120. Do they add up to 120? The individual sums? 20, 62, 92, 93, 120. So we did it right. This is one way of verifying if you got the right answer or not. In terms of ranking, we're not done yet. Now we have to find a test statistic. Test statistic here is H, and we know H is equal to 12 over n times n plus 1. Sum j equals 1 to n, in this case, 4 rj squared over nj minus 3 times n plus 1. Yes. 12 divided by 15 multiplied by 15 plus 1, 16. Rj squared, 31 squared, divided by 5. 20 squared, divided by 4. 42 squared, divided by 3. 21 squared, divided by 3. Each rank sum divided by the corresponding sample size. So rank sum for the first sample, 31, 31 squared divided by the first sample size, 5, 20 squared, second rank sum divided by the second sample size, and so forth, minus 3 times 15 plus 1, 16. What do we get? So we put it in the calculator, we end up getting 8.16. Here is a question. Is Kruskal-Wallis test a right tail test, a left tail test, or a two tail test? Which one is? Two tail test. Why is that, Jimmy? Enlighten us.
Because it says at least one of the seasons are different.
Because it says at least one of the seasons are different. Okay. Any other answers? Do we agree with you?
Yeah, the actual real example didn't state. Season was bigger than the other, it stated it different.
Yeah, that was intentional. Because I want you guys to figure it out. So is Kruskal-Wallis test a right tail test, a left tail test, or is it a two tail test?
And you said it was right because of the chi.
No, who said right?
I think you said earlier that it was right.
Well, I'm asking you.
Well, you explained that it's because of the high distribution, so it's always considered.
Let's hide paid attention. the statistic could never be negative. Yes? That number is always positive because sum of sample sizes plus 1 positive. Rank, you square it, that number will never be negative. This number is guaranteed to be bigger than that. The book goes over the derivation for a case, and we end up getting 8.16. So a Kruskal-Wallis test is always a right-tailed test. Just like let's see. We can erase the top over here. Remark it is always a right-tailed test, similar to an ANOVA, where ANOVA is the parametric version of Kruskal-Wallis. Reason being, last time I went over how we do the testing in ANOVA. It's a ratio of two things, ratio of two variances. Variances cannot be negative, so ratio of variances cannot be negative, so the test statistic must always be positive. So that's it. The rejection region has to be on one side. So in our case, I don't know what the textbook uses for notation, but the rejection region is on the right-hand side. We want to find that critical value. What should we use to find that critical value? What do we usually use? Inverse norm. Inverse norm is for large sample approximation, and we cannot use normal distribution. Question being, what do we use to find the critical value in general? Alpha. Alpha, right? We need alpha to find the critical value. Alpha in this case is 0.05. And if we want to find the exact Kruskal-Wallis test statistic, critical value, we have to use R. What we need is PKW, which stands for Kruskal-Wallis, p-value for Kruskal-Wallis. In a similar manner, QKW, it's not here, I believe they call it CKW. CKW will give you the critical value. Yes, C for critical. So you just have to use this package. I'm going to create a table for the critical values, just like I did for Wilcoxon, Steinbach, and Fisher exact site test. So in our case, what is the value of alpha? What? 0.05. And what is n? Huh? The big N, which is 15. So CKW oops, it's 0.05, comma, 15. Method. Now, if you look in the help documentation, they explain over there, it's either exact, Monte Carlo, or asymptotic. We want the exact critical value, so I'm going to use exact. What is Monte Carlo? Monte Carlo is a simulation method beyond the scope of this class, so let it be. And if n is greater than 1. So apparently, it's not the big N. They're using the individual sample sizes as a list. So C, 5, 4, 3, 3. So 5, comma, 4, comma, 3, comma, 3. Since it's an exact critical value, it is going to take some time. Hopefully, it doesn't crash. I think we broke it. I know why it's taking some response, but because it's 10,000 permutations, let me reduce it to n dot mc equals 100. Hopefully it doesn't take too much time. We'll see. While it's running, remember earlier I mentioned parametric tests can be efficient, but they do, earlier in the semester, they do suffer from issues of computation because you have to do permutations, combinations, and things like that to find the exact probability. Right now, it is trying to do one of those. The code I don't think is optimized. It's taking forever. I think we broke it. Let's see. It should work, but it's not working.
You're just gonna keep trying different ones.
Yeah, I would expect this to work because, that's just how it's done.
You have to call up your advisor.
Perhaps I should. We plan on meeting soon. But apparently he didn't write this code. Someone else. I don't know who that person is.
So in statistics, is there ever really a time where you take 4 independent variables and they all do equal each other? 'Cause it seems like if you use this test, we would just be rejecting the null all the time, because I just feel like it would be hard for all 4 to be equal to each other.
You won't be rejecting all the time. In this case, I don't think we'll be rejecting at all. Let me get the critical value. This is bothering me. Let's say, like
We have the example we did. Looks so similar. But
This one worked. I don't know why. But it worked for Monte Carlo. It didn't work for exam. You don't always reject. The rounds have to be significantly large. In other words, different for us to reject. In this case, we have the critical value to be 7.07, the upper cutoff value. The alpha level is 0.05. Our test statistic is 8.16. Did the test statistic fall in the rejection region? Yes, it did. This would imply reject null. The claim seems to be true, or there is sufficient evidence towards the claim. Now, to answer your question, Chris, the only way things are going to be very close to each other would be if some of them have the same numbers, correct? If that is the case, then if they are close to each other, or if they are the same, for instance, zeros here, you've got a bunch of zeros there, 2 zeros there, 1 there, you have to shard the rounds. When you shard the rounds, the value is going to decrease, yes? And when it decreases, that number will become not as big. So when you take away -3 times n plus 1, the resulting h value will become small. If it becomes small, you will be moving towards 0 and not rejecting. Yes, in this problem, if I change the cutoff, let's say to 0.01 significance level, I will not be rejecting the null. Does that make sense? So I was content with that 0.05 level. In that level, I'm rejecting the null. Good. Since this is a right tail test, p-value is always the area above the test statistic. So to find the p-value, we use pKw. Yes.
Since we use the Monte Carlo method, does that mean our test statistic is slightly off from the exact?
Yes. It's a simulation method. It's slightly off from the examples. P-value. The test statistic here is 8.16. Enter. Let's see what the syntax says. So X would be the data I see. So apparently, the textbook doesn't even use a way to find the p-value directly. Rather, you simply use the data, enter the data, and it gives you the p-value. So what is the data that we have? And check this out again.
I feel like that defeats the purpose.
That's basically what I said earlier.
But, you know, I have to go back and forth. It's not fully down at least, so enter all the samples. So for 5, 0, 15, 3, 7, 1, 2, 10, 4, 21, 20, 22, 7, 9, 11. I expected PKW to behave the same way as, P norm that we've done in the past or any other distribution. Apparently, it doesn't work
The
that way.
rank or
The actual data itself. So that's what it says here. So
it's 60, 12 is your last one.
thank you. 6, 8. And once you enter the data, you simply do PKW of X. Going to save it to the variable P. So it gives you the test statistic, which is 8.16. That's exactly what we had. And it's giving us the upper tail probability of 0.0202. In other words, the probability above the test statistic over there, which in our case is the p-value, is 0.0202. That makes sense. So key things to note, you cannot do critical values, p-values directly. You need that package. And obviously, from today, we realize that they don't behave in the same manner as other functions do, such as p-norm, q-norm, and so forth. Because this is written by authors external to regular R people. When in doubt, you can always, go to help, look through the documentation. I expected the exact method to work. For some reason, it's not working. You can try it at home, change the Monte Carlo part to the exact part. You will get the exact value. You're gonna ask, well, is it going to be slightly off? Absolutely, quite a tiny bit, because Monte Carlo is a simulated version. What's your question, Josh? Okay. Do we have any questions?